Okay, two new concepts. This does a lot for us. So the first derivative tells us what about a function? Click all those Chromebooks closed, please. First derivative tells us what? The slope of the tangent line. Slope, yeah, the slope of the tangent line, which really just means the slope of the curve. How steep is the curve at that point, right? Think of it if an ant's walking along the function in 2 dimensions, how steep is the slope that he's standing on? That's what the slope tells you, right? Okay, what about the second derivative? That's something different. But we can figure this out. So if the first derivative is the rate of change of the function, right? Isn't it? It's the rate of change of the function with respect to x. What's the function? Y. So how fast is y changing with respect to x? What if the rate of change of y, which is just f of x, with respect to x is 10? What's that mean? If f prime of some value of 3 happens to be 10, that's telling you the rate of change of the y value of the function with respect to x. If it's 10, that means that y is changing a lot with respect to x, right? If I move to the right a little bit, I'm moving up a lot or a little bit. If the slope is 10, if f prime is 10. A lot, right? It's a steep slope there because the function is changing a great deal. The output of the function, the y value, is changing rapidly in a positive direction with respect to x. If f prime is negative, well then that just means the y values are changing in a negative way with respect to x, and so the y values are going to be shrinking as we move to the right. We're going to be walking downhill. Well, what's the second derivative? What are we differentiating in the second derivative? The second derivative is the derivative of what? The derivative. Okay. So the second derivative is the rate of change of the first derivative with respect to x, right?
It's the rate of change of the rate of change.
It's the rate of change of the rate of change. Yeah, it's the rate of change of the first derivative. And you guys already told me the first derivative is slope. So if an ant is walking along the function, let's say, and as he's walking to the right, his slope is doing this. Is that a positive or a negative rate of change of the derivative? As he walks to the right, his slope is doing this. It's positive. How come? Because the derivative is getting bigger or smaller. There you go. So it's a positive rate of change. The derivative is growing as I move to the right. Agreed? Okay, now what if the derivative, if the tangent lines were doing this as we were walking to the right? If they were doing that, that would be a negative rate of change because the derivative is getting more negative, right? It's decreasing, it's getting more negative. How about if you did this? Still negative because the derivative is getting smaller, right? It's decreasing. Okay, think what that does to the topology here, because that's gonna change. There is a real connection between the second derivative and what the topology looks like, what the kind of terrain the ant is walking on. So I want you to think about this one. We're going to take a little longer journey this time. So I'm starting off, this is the derivative. Positive or negative rate of change of the derivative? Positive, so the second derivative was positive. Think what kind of terrain that would be. If I started off out here to the left, I started off with a steep negative slope, and gradually as I walked to the right, it got more positive. It's a valley, isn't it? Right? It's a valley, and the fact that the tangent line was gradually increasing means that the terrain had to be kind of dish-shaped upward. We'd say that it had an upward concavity, right? What does a concavity mean? Like a bowl or a depression, exactly. So the concavity is upward. We call that a positive concavity because it's a positive rate of change of the first derivative, and that's the characteristic of a positive second derivative. A region where the second derivative is positive is going to be a region where the curve has an upward disc shape to it. It's concave up. Now think about the opposite. Think about this. What if I started off like this? So I'm on a steep positive slope. And as I walk to the right, my derivative is decreasing like that. Well, what kind of terrain did I just describe if I went from that to that? Okay, that would be something like a peak, wouldn't it? But most importantly, it would have a downward concavity, right? I'd have a bowl that's pointing downward. It'd be kind of a disc-shaped down shape to the function, right? Okay, so let's look at this in a little more detail. So the second derivative is the rate of change of the first derivative with respect to x. So it's the rate of change of the slope with respect to x. When the second derivative is positive, case 1, the slope of the function increases with increasing x. This implies that positive slopes become increasingly positive, so they get steeper, and negative slopes become less negative, right? That results in an upward concavity. It's disc-shaped up. So that would be something like, that's going to tend to look like that, right? And then conversely, if the second derivative is negative, the slope of the function decreases with increasing x. This means that positive slopes become decreasingly positive, and negative slopes get more negative. They become increasingly negative, which is going to result in something like that as I move from left to right. Okay? So let's explore this with Desmos. So what do we got here? We've got a function, f of x. It's a cubic polynomial right here. And here's a point. You can see the coordinates of the point as I slide this thing across. Right? Okay, I got a couple other things. So I've got a vertical line, a vertical purple line that just helps us keep track of where we are on the x-axis. And then I've got a tangent line that dynamically moves with that point of tangency as we move along. Okay, make sense? Okay, so then everybody agree that, you tell me, so if I go from that point right there to the right, is the slope increasing or decreasing? Decreasing. Still decreasing, isn't it? So what should the sign of the second derivative be there probably then? Negative, yeah. Okay, tell me when you think it changes. Yeah, somewhere like right in there, huh? Somewhere right in there is where it changes from decreasing to increasing. Right, now the second derivative becomes positive. So what do we call that thing? See if you remember. What's that special point in the middle? An inflection point, yeah. That's an inflection point. What is an inflection point? An inflection point is a place where the concavity changes, where it transitions from positive to negative or vice versa. Okay, what I want you to see here, and I'll reference this again and again, but this really helps conceptually. The second derivative relates to slope in the same way that the first derivative relates to y values, right? So we said that a point is a relative maximum if it's a place where what transitions? The relative maximum, if what? If the derivative is changing sign from positive to negative or negative to positive. So a relative maximum would be the derivative is changing from positive to negative, right? I'm going from an increasing to a decreasing function. That's our first derivative test. A valley would be a place where the derivative is changing from negative to positive, right? Okay, well, an inflection point is just the analog of that for second derivatives, right? If I'm changing from upward concavity to downward concavity, the place where that happens, where the second derivative transition sign, is an inflection point. okay? Or vice versa. I could go from downward concavity to upward concavity too. We don't give them, like we do a relative maximum and a relative minimum in the case of extrema. We give them different names. We don't do that for inflection points. They're just inflection points. Have you ever heard people talk about inflection points though? I haven't heard that like when you watch the news or something. You ever heard people talk about inflection points in the economy? Well, people do like pay attention, and you'll notice that it is something that comes up. People use them incorrectly a lot, but when you listen to like people that are smart, that know what they're talking about, and they talk about the economy, or they talk about population growth, things like that, where they're using the terms correctly, typically they're going to be economists or scientists or mathematicians. When they say inflection point, they mean inflection point. They mean what we're talking about. There's something really important about an inflection point. When we get into optimization stuff, which is going to be our next kind of big, differential calculus application. It's the really important one. We'll talk about applications of economics, and it turns out that inflection points a lot of times are more important than extrema. And we'll talk about it when we get there. But okay, here's another one. Look at this one. How about something like this? So I've got, let me go back to, I want to flip this back to 2. Okay. So there's a function, right? What kind of function is that? Quadratic, yeah, okay. So that's the function. This is, I'm going to graph in red, I'm going to graph the first derivative. Okay, does that make sense? Right, it does make sense, doesn't it? Because the first derivative is 0 where we have a horizontal tangent line, and you can see that the first derivative is transitioning from negative values to positive values, which by our first derivative test tells us that this is a valley, right? Okay, here's the second derivative. Doesn't that make sense? It's the derivative of the first derivative. Well, the first derivative is a line with a positive slope, so doesn't it make sense that its derivative is positive and constant? Because the slope is always the same, right? So if the second derivative is always positive, then that means that this function is always concave up. That's true though, isn't it? A parabola is always going to be dish-shaped either up or down, either concave up or down. It could never change. Because this parabola opens up, it's always concave up. It always has positive concavity. So the second derivative is always positive valued. Okay, let's compare that to, how about a function like that, the cubic function? Okay, does this make sense that that would be the first derivative? It does, doesn't it? For many reasons. First of all, because we would have to transition from a cubic to a quadratic. But more importantly, you can see that the zeros of the first derivative have to correspond to the horizontal tangents of the function, right? In any place where the green function is increasing, those are going to be the places where the red derivative is positive valued. Right? It's going to be above the x-axis, right? The places where the ant is walking downhill, where the function is decreasing, would be where the derivative is negative valued. Okay, give me thumbs on that. Everybody see that? Okay, so what's the second derivative going to look like? Yeah, it's going to be a line. It's going to go, the rate of change of, well, what's the slope doing? It's going from very negative values to very positive values, right? So then the second derivative function must be going linearly from negative values to positive values. Can anybody estimate for me where the point of inflection is on that green curve? What is it? That's a pretty good guess, right? It's right there, isn't it? Everybody see that? How come it's right there? Okay, sure. It's where the concavity changes. That's where we change from being bowl-shaped down to bowl-shaped up. But the easiest way to see it is by looking at the second derivative function, which is the blue function. Yeah, it's going to be the 0 of the second derivative, right? where the second derivative passes from below to above the x-axis, from negative to positive values. Everybody see that? Okay. All right. Okay, so is that a point of inflection? Yeah, it seems to be, doesn't it? Give me thumbs, top one. What do you think? Yeah, good. Okay. How about that one? Right there. Okay, you're right. How come? That's a tricky one. I'm surprised anybody... Well, it is changing concavity, isn't it? It's changing from downward to upward. Okay, but what's the problem? We have a sharp corner there. So why, tell me, why couldn't the second derivative... It's undefined, isn't it? If the first derivative is undefined there, then how could you take a derivative of the first derivative where the first derivative doesn't even exist, right? So that is not an inflection point, and this is a really common source of misunderstanding for first-year calculus students. This comes up all the time, and I don't know that this is ever really addressed. It might be in the book, but a lot of them, it's not a lot of times. This is a great definition of an inflection point. An inflection point is a point where the graph of the function has a tangent line and where the concavity changes. It's not just where the concavity changes, it's where the concavity changes and a tangent line exists. You see that there is no tangent line there because the derivative doesn't exist, right? Tangent line can only exist where the derivative has a value where it exists, okay? So another way of saying that would be where the first derivative is defined and the concavity changes. Okay? Give me thumbs on that. Does that make sense? Okay. So let's just practice some more of this stuff. So I want you guys to tell me, there are a bunch of different cases here, and you get to choose which of these graphs represents. You only have, I guess, 4 choices for case A. So what's going on at A? Tell me what that means. The function is positive valued, first derivative is negative valued, and the second derivative is negative valued. So I want you to tell me which of those, think about it, discuss it with your neighbor here real briefly. I want to know which of those could be A. You're going to vote 1, 2, 3, or 4. First, second, third, or fourth. We're looking at this guy right here. Third one? Okay, you going to shoot that one down?
Yeah.
Why?
Because the slope is positive.
Oh, yeah, look, the slope has to be negative. Okay. Fourth one. Has to be the fourth one, doesn't it? Okay, what does it mean that the function's positive valued? Above the x-axis, so we could cross out a bunch of them. The fact that the first derivative is negative valued. Decreasing. Ants walking downhill. The second derivative is negative valued. So what's it mean about the concavity? Concave down, right? Okay. So what's a really quick and easy way of determining if it's concave up or down? Like, explain to me why that's concave down.
Down in the ground. It looks like an upside down ball.
Okay, because it's bowl-shaped down. Yeah. That's a great way to do it. I'm going to show you another way that I think is the easiest and best way of doing it when you're looking at a function where it's just not obvious which way that it's bowl-shaped. Look at a tangent line. So a tangent line to this function at that point, look at that tangent line compared to that tangent line. What's the difference? Say it again.
Fourth one has a negative tangent line versus the one.
Okay, I'll tell you what. It does not have to do with the sign of the slope, though. It doesn't. It just happens to be a decreasing function there, but it could be increasing just as like, for example. Okay, yeah, there you go. If the tangent line sits on top of the curve, then that means it's concave down. It's negative concavity. If the tangent line at a certain point sits below the function, then that means that the concavity is positive. It's concave up. Anybody get that test? Okay. All right, so what about case B? So now we're looking at this guy. Go. Look at those and tell me which one of those is B. Show me with your fingers and I'll give you. Yeah. Oh, which one is it? There you go. Yep. Okay, so the answer is 4. Has to be this guy, right? How come? Because it is below the x-axis, increasing function, concave up. So tangent line should sit above or below? Below. There you go. It's got to be number 4. Okay? Okay, how about C? It's getting quick. Okay, it's 3, isn't it? Right? Because it's below the x-axis, increasing function, concave down. So tangent lines sit on top. Yeah, so it'd have to be that guy. Okay. Real quick, which one's D? Right? 2? Okay. Which one's E? Yeah, 4, isn't it? Okay. All right, you got the idea. We can probably skip through some of those. Now we can skip these. You got the idea. Boy, I had lots of those, didn't I? Okay, so the figure to the right shows the graph of a function, match the function with its first and second derivative, okay? Okay, yeah, I didn't mean for that to be filled in. Yep, go ahead. Okay, so let's do this. Let's sketch the first and second derivative. There's the function. Let's sketch the first and second derivative. Okay, well, what are some points? If I want to graph the derivative function, what are some points that where I know the value of the derivative? At 0. What's the value of the derivative at 0? 0, because it's a horizontal tangent, right? Okay, so we know we have a point there. To the left of 0, for negative values, what's the function doing? Is it, as I go to the left, is it going to be negative or positive? Oh, it's going to be negative. As I go to the right, what's it going to do? It's going to be negative again, isn't it? Yeah. So what's that going to look like? Yeah, like an upside down parabola, isn't it? It's going to do something like that. There's f prime. So what is the second derivative going to look like then? It's a line that's going from positive to, okay. And I know its value at one place. What's that? At the origin, right? Because that's where the derivative is equal, the derivative of this function is equal to 0, right? Okay. Does that make sense in terms of concavity? It does, doesn't it? We're going from a region of positive concavity, where it's bowl-shaped up, tangent lines sit below the curve, to a region of negative concavity, where it's bowl-shaped down and tangents sit on top of the curve. Right? Okay. All right, hold that thought. Okay, so okay, what about this one? So I'm giving you the first derivative and the second derivative, and I want you to tell me what the function is. So which one of those, we'll call this, just moving from like reading a book, like 1, 2, 3, 4. Which one of those could it be? I guess I got to make it a little bit smaller, don't I? There are the first and second derivatives. I want to know which of these is the correct graph. Here, I guess I can just do that. We don't really need to see there. Which one of those is right? Talk about it. Okay, what do you think about this first one? Well, let's look at that first one. So first of all, let's look at so we're trying to pick the correct green graph, right? Okay, does that green graph, does it seem to match up with the blue graph?
No.
What's wrong with it?
It goes down and the other one goes up.
Oh, the zeros.
Yeah, it's backwards, isn't it? Everybody see that? Look, you might be tricked into thinking it's okay because look, you have a horizontal tangent there. Oh, that lines up. You have a horizontal tangent there that lines up. And you have a horizontal tangent there that lines up. But the signs are wrong, aren't they? Right? Where the derivative is positive valued, the slope should be doing what? If the derivative is positive, the function should be doing what? Increasing, right? It's not doing that. The function, the ant's walking downhill where the derivative should have a positive value, so that can't be it. Agreed? How about the second derivative? The second derivative, let's see, where the second derivative is negative, this should be bowl-shaped down. Is it? No, right? Where the second derivative is positive, it should be bowl-shaped up. No, it's bowl-shaped down. So this thing is, what do I probably need to do to this thing? Yeah, I just need to reflect it, don't I? Right? So which one seems to do that? Yeah, that one seems to be a reflection. Let's look at this guy. Right? Everybody see what I mean? We took this thing and we just reflected it around. Flipped it upside down. Okay, does this work? Let's check the blue function out. So again, we've got, let's see, we have a place where we have a horizontal tangent that lines up. Horizontal tangent. Horizontal tangent, that's all good. How about concavity? Look, it looks to me like if we look at the concavity, it's going to be negative concavity, so bowl-shaped down to the left of that dashed line. Give me thumbs on that. Does that make sense? Seems to be right. We should get between those zeros of the second derivative, we have positive valued second derivative, so it should be bowl-shaped up. Well, that makes sense, right? Tangent lines would sit below the green function between those dashed lines. And then to the right, we should get concave down again, which it looks like we do, right? It's bowl-shaped down. Okay, make sense? So if the concavities match and we had the correct horizontal tangents, the rest of it has to work, honestly. We can show that it does. Look what happens here. The function has negative value, so it should be increasing to that point. It is. Then the derivative has negative value, so it should be decreasing for an interval. And then it flips back to increasing, and then back to decreasing. So that's the winner, isn't it? Okay, make sense? I mean, there's a lot of, probably got to look at this, go back and look at the notes again. I mean, this stuff, it's just a lot to take in. But that is a huge advantage. If you can kind of conceptually weave those concepts together, it makes the rest of the class a lot easier, right? So that's kind of an important thing to be able to feel comfortable with. Okay. Okay, so what is, I don't think I ever told you. So what do you think the second derivative test is then?
Testing the second derivative.
Let's see if we can build this together. I want you to think about, I'll tell you what, I'm going to do it. We're just going to do a problem that asks us to use this second derivative test. We don't even know what it is, but I bet we can come up with it. So here's a problem, just exactly like the kinds of problems you guys have been looking at, right? Where we're going to try to make a table, and we're going to come up with a sketch from this. We want to find out all the places where we have local maxima, local minima. Let's find out where it's increasing and decreasing. Let's see if we can find some points of inflection. Let's find it all. A whole ball of wax here. So what's our domain of this function? F of x. All reals. It's a polynomial, right? So you know it's all reals. There's no problems with this at all. Domain, all reals. Does it have any symmetry? No. How come? You're right. Yeah, I'm mixing even and odd exponents, so it destroys the symmetry, right? So there's no symmetry, okay? We need some derivatives, don't we? Right? What's our first derivative? Minus. Okay. Let's go ahead and factor that while we're at it.
Negative 9x times x plus 2.
Okay, good. Now when we want to take our second derivative, we want to go back from this row, don't we? We don't want to do a product rule. Okay. What's our second derivative? If I factor that, what do I get?
Negative 18 times x plus 1.
Okay. So let's make our table. Okay, only now we get to add an extra row to our table. We're adding a second derivative row, right? Okay, you told me correctly that our domain was all reals. Okay, what are my first derivative critical numbers going to be? What are they going to be? 0 and negative 2. Yeah, okay, good. So we know that f prime equals 0 when x equals 0 or negative 2, right? Those are the zeros of our first derivative. Okay, so negative 2 and 0. Where is the second derivative equal to 0? Say it again? Negative 1. Okay, and those were negative 2 and 0 were zeros of the first derivative. Negative 1 was a 0 of the second derivative, right? Okay, so let's figure out what's going on using our first derivative test. Okay. However, what you're going to find is we're going to develop the second derivative test, which is superior to the first derivative test. It's going to supersede the first derivative test, except when, I like to leave you hanging. Yeah.